Thank you for dealing with my frazzledness here. It's an interesting morning. Okay, so yesterday we went through, this is kind of where we got to the point where we were speaking to the activity series. So in this cell right here, we had silver nitrate, and then we had copper metal, and this occurred spontaneously, meaning this reaction in the way it is written, copper plus silver ion, was a spontaneous or thermodynamically favorable process. Delta G is negative, and then this is like considered a galvanic situation. It's just we have not separated it into two chambers, therefore it's not like an accessible amount of energy. It's just the electrons are being traded off in solution, and we can't capture those electrons at all. How do we have to set up a battery to capture electrons? We need an external wire, so we need them in two separate chambers to make this work. So that's what we're going to do here. We're going to we're going to write the NIE, we're going to write the half reactions, we're going to draw our battery, we're going to make sure we know which one's the anode, which one's the cathode, the whole gamut. And so this is what I expect that you're able to do given any situation now when I state it's a cell or it's a galvanic cell. So in that reaction, it was solid copper and a solution of silver nitrate. So what's the full reaction? Cu solid, Cu solid plus what? Silver. I'll put silver nitrate for now. Keep going. Aqueous. So copper 2, and then the nitrate's going to be a spectator. So I'll put that inclusively together. I'm just going to put silver first. Okay, so from this, though, we know that copper and silver were both species involved in the redox couple. And then from there, we have nitrates kind of hanging out. Balance this out first. 2 in front of silver and, okay, and then who's our spectator? Nitrate. So I'm just going to cancel nitrate and notice that there's 2 nitrates there because of the 2 coefficient, and then there's 2 nitrates here because of the subscript. So now refresh this and rewrite it as like an NIE with the ions. How do I finish this? Cu solid, 2Ag, 1 plus, because they are technically in ion form at that point, yields copper 2 plus and 2Ag solids. Okay, which of these processes is the reduction? So we might need to assign oxidation states, or just kind of check it out. The silver went from a silver 1 plus to a silver 0, right? Free element to 0. So if I went from 1 plus to 0, I went down in oxidation state, so I gained electrons. So reduction is silver ion yielding silver. Where does the electron go for this half reaction? In the reactants. Good. So 1 plus and 1 electron will make silver solid. And then what's the oxidation half reaction? Cu solid yields 2 plus and 2 electrons. So that's showing the loss of 2 electrons in the products. This is showing the gain of 1 electron in the reactants. And then I'm not asking for you to balance this out right now because we actually already have the balanced entire NIE. These are just the half reactions, but we know that there's got to be 2 electrons lost and gained. Question? If it's just asking for the half reaction, it's just asking for you to identify who's oxidized and reduced. But if it wants the full NIE, which would be the balance form, charge and mass, it would be this right here. Okay? All right, so in terms of just definitional items here, we've already said this once, but the anode is where our oxidation process is occurring. So who or which half reactions are occurring at the anode? The copper. So the anode is the oxidation half reaction. And then which process is happening at the cathode? Okay, the reduction, so the silver. So what we would see in the essence of like visualization of the chemistry here, we would have a copper solid piece of electrode, and then over time, so this is like sitting in its own little chamber, and then in this solution we have copper 2 floating around, right? So over the course of this reaction, what is happening to that copper solid? It's ionizing. So what do you think is happening to this copper solid piece? It's breaking apart, it's dissipating, it's disappearing. But it's not really disappearing. What is it becoming? Ion, right? So what we do is we draw like a little V shape to say that it's like disappearing, it's like dissipating away. And as that occurs, it's depositing in its own solution more copper 2, more copper 2, more copper 2. So much copper 2, we start to see this solution turn what? Blue, right? It was blue to begin with because copper 2 is in it. But we all know now that copper 2 is blue, and so it's becoming deeper and deeper and deeper blue. And so that's just because we know what copper 2 looks like. We know that we can see this solid dissipating to its aqueous form. So we actually kind of draw that sometimes on our models to say, I know what's happening at this anode. And then vice versa, I should know what's happening at the cathode. So for the cathode, here's my little chamber. Here's my silver. What's happening to that? Oh, sorry, silver ions just hanging out in solution. What's happening to the silver over the course of this reaction? Say again? Well, I don't want to use the word deionizing because I want you to tell me what that, because that's hard to know what it looks like. What do you mean? It's precipitating on the silver, right? This silver ion is taking an extra electron and it's becoming silver solid. So I call it like a little beard. It kind of just beards up or precipitates on the silver metal. So it kind of clumps on the silver metal. So you can see it as like little silver particles. And then over time, this silver ion, which is now depositing, that's a better word, depositing on the silver, what becomes of the silver ion concentration? Decreases silver ion concentration. Now, there's no color change because silver is what? Clear in solution, so you wouldn't be able to see anything. It's just, it would be like less conductive over time, the concentration decreases and so forth. I'm going to draw these better in just a second. Yeah. From the anode. So this copper, that's just releasing electrons. It's going through the external wire and depositing on the other side. So I do these separately so you can see the differences, but I'm going to draw the whole scale picture in a second. So, speaking of the whole scale picture, I'm just going to go down first. I'll come right back to this. So we drew one picture yesterday. Oh, we didn't get to finish the whole idea. So here are our two chambers. Here's our copper. And it doesn't matter if you put copper or silver on which side or the other, as long as you label them correctly. Okay, so practice drawing with me because you're going to draw these, like 5 of them in a couple minutes. So these are solid electrodes. The solid electrodes are connected with an external wire. And so they're just like connected to the solid pieces. It's like a piece of conductive metal. And in our beakers, we have a solution that these are sitting in. And are sitting in their own ion solution. So this is sitting in what? Copper 2, and it's copper 2 nitrate, but I exclude the nitrate because it's not relevant here yet. And then this is sitting in silver ion or silver nitrate. And what's connecting them as well? Salt bridge. So it doesn't have to be pretty. It's just like a little connection of sorts. And it's got electrolytes in it. And those electrolytes we called yesterday we called out a very specific electrolyte yesterday. Do you remember what it was? Potassium nitrate. And so in that aqueous form of potassium nitrate, we actually don't have potassium nitrate. What do we have actually? Potassium ion and nitrate ion. So what those items in the salt bridge will do is they'll help neutralize the charge buildup that occurs on each side of this battery. So now that we know this, we know that this is the copper going to copper 2 plus 2 electrons. So what's occurring is actually this copper solid is losing electrons not to its own solution, but through the wire. The electrons flow, 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 and as they get traded to silver, silver now has this buildup of negative charge on it, which are electrons. So this little silver guy, ion, will come and capture one. And as it comes in and grabs the electron, it just deposits itself on that metal. That's it. And it'll keep going and going and going. And so over time, that's what we say there's a copper electrode kind of dissipation. So we kind of draw this little V shape to say that like it's disappearing. And then as this copper, and I didn't state this earlier, as it loses its electrons up here, itself can't maintain its solid state because it's no longer a neutral salt, like a neutral atom. Once it lost 2 electrons, what does it become? An ion, right? So there's more and more copper 2 just depositing into solution as it continues to lose its electrons through the wire. So that's what we see that like really bold blue color over time here. And then, like you guys said, the silver will deposit. So there'll be like little flakes of silver that kind of just builds up here as all these silver ions jump on board and they deposit on their silver electrode. Are we okay so far in understanding the anatomy of this? All right, so yesterday, just as a quick review, we stated as the copper loses electrons, what buildup of charge occurs over here? Look, it gets more positive, right? Because you're just like losing electrons, you get more positive. So as it becomes more positive, which ion from the salt bridge matriculates this way? The nitrate to say, okay, look, can't build up charge because you're going to stop the process and we can't have a battery stopping. And then as the electrons flow this way, this becomes more negative. And then as that process occurs, who neutralizes that charge buildup? The potassium. And the potassium just flows through the salt bridge and kind of just hangs out here to help neutralize that process. We good? All right, so it's an intricate drawing. There's a lot to it, yeah. Because if you keep building up a positive charge here, copper will never lose more electrons because it will actually have an attraction for its own electrons, and it will not allow electricity or electrons to flow through. And so we as humans, we're right here, and we're like looking to see the electrons because we want those electrons, and so we kind of siphon them off to capture them, so then the battery would just stop. It would be a dead battery. But yeah, there's actually a voltmeter here because we'd like to know how much energy our batteries are producing. So like a 9-volt battery or something like that, you could test it with a voltmeter and it hopefully reads 9 volts. And that's where we would then put our voltmeter, put some way to siphon off those electrons. And then, I was going to tell you something else. Oh, we have to label this the wet chamber, anode or cathode. Anode chamber, and we've labeled this the cathode chamber. So instead of drawing this every single time, sometimes it'll ask you to do the line notation. And the line notation is just as was written right here. So you write the anode solid, like a solid electrode first. Oops. And you put a line, and you put what's in the chamber, like the liquid aqueous stuff. So what's the solid electrode on the anode here? Copper. They put a line, and then what's in the copper chamber? Copper 2+. I'm not going to put the nitrate because I don't care about the nitrate. It's a spectator. We're looking for the redox couples here. And you draw a double line, which represents salt bridge. And then you say, okay, what's touching the salt bridge, which would be the other ion aqueous stuff in the cathode chamber, which is what here? Silver 1+. And then we draw a line. We say, okay, what's the solid electrode in the cathode chamber? Silver. So this is much simpler, but it gives me the same information. And so sometimes it asks for line notation, sometimes it'll ask for the diagram. All right, thumbs up when I can move on. You guys write down the salt bridge purpose. It's here in purple. I've said it like 3 times, but it's mainly, it is it's like an FRQ question, like it'd be part of an FRQ, like why is the salt bridge important? Or which ion will flow towards the cathode in the salt bridge? Like there's some purpose to this here, okay? Who's absent? Good question, right? Who? He is. Just has. Okay, so, this was the video I had started to show you guys yesterday. I think it helps a lot with understanding the pieces to this.
Zoom into the atomic scale and see how this cell operates. Here, at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution. Each atom loses 2 electrons and becomes a zinc ion, which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper 2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom, which deposits on the bar. Therefore, as the cell runs, the zinc anode becomes lighter and the copper cathode heavier. Now let's close in to see the role of the salt bridge. The non-reactive sodium and nitrate ions of the salt bridge prevent the buildup of charge that would occur as zinc ions enter the anode solution and copper-2 ions leave the cathode solution. Such a charge buildup would halt cell operation. In the anode compartment, nitrate ions leave the salt bridge to balance the gain of positive charge as zinc ions enter the solution. Some zinc ions also enter the salt bridge. In the cathode compartment, sodium ions leave the salt bridge and nitrate ions enter it to balance the loss of positive charge as copper-2 ions leave the solution and are reduced at the cathode.
All right, so that one's cool, but I have an even cooler one. Okay, so my husband found this, and I was like, this has to be shown. It's beautiful. So I want you to think about what, this is a redox reaction. What metals are these? What does it look like? Maybe. Wait for it. So that's silver growing like another electrode that's depositing. It looks like a tree branch appearance. And the copper's being eaten away because it's giving up electrons. Guess what we did our free time? Here's another one. I think the music's also good. So this is lead and zinc. See, like either way, they're turning electrons out. Okay. So zinc is the artificial or the sacrificial anode, which is the bottom piece that's being eaten away. That's lead. Look how cool that is! Like, this is cool. Okay. I think there's one more. Hold on. Never mind. That was it. Yep. All right. Beautyofscience.com. Okay, so I think now you know how to sketch. In terms of, there's one like caveat. If you don't have metals, because technically you can have redox without metals. You can have like two ions, like dichromate, dichromate, like we spoke of yesterday. You still need an electrode to like help the electrons flow to the external wire. So make sure you write down this piece here. If you don't have solid metals, you need to use either graphite, which you could just put a C, meaning carbon, or PT for platinum, because those would be two inert species that would not be included in the redox process, but they are conductors, therefore they grab the electrons and they help them get transported over to the other side through the external wire. So they basically help with transport because they're conductors. And every single time we draw a battery or galvanic or electrolytic, every single time electrons will flow from what to what? Anode to cathode, because that piece is showing the loss of electrons and then the gain of electrons, meaning that you're losing them and then they're being gained by the other side. Every single time you draw a cell, include the half reactions, like I modeled, tell you that just a minute ago, the half reactions, the full reaction, the cell potential, which I'll talk about in just a second, and then the diagram or the line notation, as it's also called. I'll show you guys a funky air cell later, but I want you guys to practice a couple of these first, okay? And I'm gonna look on this paper. I'm pretty sure I put down. Yeah, okay. At the upper right-hand side of your notes, like your packet of notes, you'll find some of this, actually someplace there. But the ones I'd like for you guys to draw, can I move past this? Almost. Okay. The ones I want you guys to draw are, hold on, are these, okay? So what I'll ask is you, first, I want to draw another practice one, but we are going to draw these shortly, okay? So I'm going to draw one here. This one, okay? So give yourself a sketch, just so you can have your template. It doesn't have to be beautiful. And see if you can predict, given that's a galvanic reaction, predict what products will be produced here. All right, any predictions on our products here? CJ's table, help me out. Okay, so we're doing a similar replacement reaction. We're making aluminum chloride, AlCl3, crisscrossing charges, and what? Tin. So you're saying tin solid, right? So we need to verify that we have an oxidation and a reduction process here. So let's break those down into half reactions and ensure that. Marcus, get me started.
Aluminum solid to aluminum solid.
Okay, and
Tin.
hold on, and
And
okay, and go ahead and tin.
Tin plus ion.
What? 2 plus ion, good.
To tin solid.
And we should then have electrons where here?
On one side, two.
Good. So we have an oxidation reduction. So you have to verify that before you get too deep in the drawings. So we do know that there is a transfer of 6 electrons total. So like, I mean, I would multiply it to balance this out totally. I would get 2 electrons. I mean, 2 times 3, 3 times 2. So I could total this up to be a 2 on the aluminum, a 3 on the tin, a 2 here, and a 3 here. So that would be our balanced equation. But overall, we're looking for half reactions, so we know how our oxidation reduction will occur. So what do you guys have a preference? Anode, cathode, cathode, anode? You want to keep drawing anode, cathode? Okay. Now, just understand it will not always be given that way to you, so please don't fear the change. So this will be what? If you're calling this the anode over here, who's anode? Okay, so I'm going to put oxidation here because we can see the loss of electrons. This is the anode. And then this one must be reduction because we have a gain of 2 electrons, or 6 overall. And then that's the cathode. Okay, so this will be aluminum. This will be tin. So they have to be the solids on the electrode sides. And then down here will be what? Say again? Aluminum ion and tin ion, and there'll be a bunch of them, but I'm showing one. And this will be our anode, and this will be our cathode. Okay, and then how do electrons flow? From the anode to the cathode, and you should draw like not one arrow, draw two arrows so it's very clear like how you're flowing electrons. And this salt bridge is down low. You also can draw it like a bridge. That's usually how I draw it. You can see maybe on the bottom down here. It's just connected. And there's a reason I have a negative and a positive here because I'm already showing you which side is flowing this way from the salt bridge. Because it lost electrons, right? So it's getting more positive so that the anion is flowing towards the anode and the cation is flowing towards the cathode. Did you hear that? Anion towards the anode, AA, and then cation towards the cathode, CC. So you really can't mess up there. I'm going to show you cell potential next. Yeah. You don't have to. Sometimes it's helpful to verify, like, you know how the changes are occurring. Because FRQ questions based on this would be like, draw the cell, done. How is the mass of the aluminum electrode changing over time? You should know the mass of this is going to decrease over time because of the nature of how that is affected by oxidation. Or how is the mass of the tin electrode changing over time? You should know that's building up in mass over time. So, like, there are FRQ questions that come with those. Yeah.
For the cell line diagram, which way is it?
On your paper, I think maybe it fixed it since I've typed up your own notes. So you guys tell me the cell diagram or the cell line notation for this one. Aluminum, line, aluminum, 3+, line, oops, 10, I wasn't write copper. Oh. Okay, so 10, 2+, because that's the chamber, and then 10. Okay, so this is the line notation. Follow those that we just went over here. Okay. All right, so cell potential. Basically, like, different batteries have different voltages they can put out because they have a difference in how willing they are to give up their electrons. So we want to compare how willing is aluminum able to give up its electron versus how much tin wants the electron. So there's a pool here called the reduction potential. Notice I'm not saying oxidation potential. So the reduction potential is how willing is aluminum to give up versus how willing is tin to accept the electrons. The bigger the difference between them, the more the voltage, because there's a rapid flow of electrons occurring. If there's not much difference between them, it's a slow flow of electrons just because there's no, like, push to make the electrons move. So the way we get these numbers are from the reduction potential list, which I gave you guys a really inclusive one. Find this. So let's look for our two half reactions on here. I do want you to underline or star or highlight one word on this paper. It's the word reduction. Reduction. So how are all of these half reactions written? They're written as what? They're all written as reduction half reactions. We have no oxidation potentials. It's not a thing. We could make it, like, I could tell you how to do it ourselves, but you'll never have you'll never have an oxidation potential list, period. We only ever compare the reduction potentials, or the ability of something to gain electrons. So look for aluminum, and and its counter ion, aluminum 3+. Look for that here. And what is the number associated with it? Okay, so I'm going to write that in my area up here. So it's called E. Okay, E is our label for reduction potential. So let's go with E for now. E for the aluminum is negative 1.66 volts. Please help your partner find that if they did not find it. It's alpha order, so it's like in the, what's up? Right, so here's the deal. I don't care if this half reaction that we have written is oxidation or reduction. We are looking at the nature of that ion or that metal, and we're looking at the nature of it as a reduction sense and saying how likely is it to reduce. Does not matter if it's oxidized, okay? So we only look at reduction potentials. What is the reduction potential of tin and tin 2? Say it one more time. And these are volts. V is volts. right, so we're going to talk about what these numbers mean more in depthly in a second, but I want to make sure you can calculate, find them and then calculate with them. So what we look at is we look at the difference between the reduction potentials of the oxidative and the reductive half reactions, but we have to calculate it one way. And it's, can I move down from here? Okay, it is E red minus E ox. So E red, which is the reduction half reaction, or the reduction, yeah, half reaction, minus E ox, which is the oxidation half reaction. So, I don't know if you're picking this up, but it's redox. Redox, okay? That order, not ox red, redox. Alright, so E red minus E ox is equal to E cell, meaning the cell potential, meaning how good is this battery? How many volts can it make? So all I want to do is plug in the reduction half reaction number, which was what? Was it negative? I thought Marcus said negative. I just lost. Where's it out on this paper? Thanks, okay. So negative 0.136 volts is for the tin electrode. We're taking that and we're subtracting what? Negative 1.66 volts. And that's for the aluminum half reaction, or the aluminum electrode. So once you've identified who's red or reduced and who's oxidized, you plug their reduction potentials in. You find their overall difference, which is what? .5 what? 24. And then what's the unit here? Volts. Okay. So E cell, which is the cell potential, which is the difference in the reduction potentials of these two scenarios, of these two electrodes, tells us that with this battery at standard conditions, which I'll tell you what that is too, the standard conditions will give us 1.5 volts. Pretty good battery. Not bad. That's like what a little double A is, about 1.5 volts. So you have to do what minus what though? Okay, so the reduction half reaction minus the oxidation half reaction. So you change these numbers. Doesn't matter if it's oxidized or reduced. Take the reduction potential and subtract. All right, I want you guys to try a couple. So now let's go to the ones that I just had for you. Let's do like 2 or 3 of these though. I want you guys to do 1 and 3 right now, okay? Start with those. I'm intentionally giving you non-metal ones because we've just done 2 or 3 metal ones. No, I want you to do the whole thing. Sketch and describe the galvanic cells. Give the line mutation. Give me the cell potential. Take a couple minutes right now. All the details. Because this was your homework last night, and if we can knock this out, this is good for you. You have it on your paper? Where's your copy? What was the other? One second. Alright. Okay, we're not quite done yet, but here we go. So half reaction, oxidation should be the chromium one. Check. And that's because of loss of electrons. You should be able to quickly identify oxidation reduction. Cathode is the chlorine one because it was gaining 2 electrons. And I put platinum on both my electrodes because we had no solids at all involved. And then all the ions or gases are included in solution. I just put a circle around the bubbles to make them look like gases. And then once you have those included, and you're, I'm going with the same flow you guys want to, anode to cathode, showing our electron flow. The ions are already listed in Saltbridge in this picture here. Your line notation is weird. You put platinum because that is your solid electrode. Like, I know it's not the piece that's involved in redox, but that is your solid electrode. You put the ion forms in your aqueous chamber, double line for Saltbridge, and then chlorine gas and chloride in your chamber, and then platinum again as your electrode. Okay, let's do cell potential here, which is your E cell, which is E red minus E ox. So E cell is equal to E red minus E ox. What is the number associated with the reduction half reaction? Loud and proud for me, I'm sorry. 0.359? 1.359 volts, and that's for chlorine. We're not flipping numbers, we're not changing things, it's just reading right off the chart. And then what's the reduction potential for the anode? 1.33 volts. Right, so both of these are positive in this case, okay? And then I'm going to plug those numbers in. So what's this first one? 1.359 volts, and then the other? 1.33 volts, and then what's our difference? Wait, what? Alright, look at that really hefty battery there. It's like basically making no volts, right? This would be a horrible battery because we would be like, there's not a great potential for electron flow. Chromium's like, I mean, yeah, like, I kind of want my electrons, and chlorine's like, I mean, I'm cool with not having the electrons, so they really don't want let the electrons flow. So this potential is low, but it's positive, which is important. Okay? So, well, I want you to note 2 things so far. Every single time between, the 2 times we've done reduction potential now. Questions here first? Yes. I just got crazy and I drew 2 over there. There's no method. You could draw 15 as long as they were in some sort of ratio. I just had room, so I wanted to draw more. Okay, so both times we have found cell potential, they have been what here? Positive. Okay, so this was, that's not negative. What does that say? Oh, that was the, I was like, that is not negative. This was the cell potential. It was positive, right? Okay, and then this one is positive. So what do you know about galvanic cells? They will always make a positive cell potential, okay? And then the way we have always achieved that is by taking reduction minus oxidation half reactions, but the reduction potential is always higher or lower? Higher, right. The way you can predict it, if I give you like cell potentials and I don't tell you who's oxidized and who's reduced, you always have to take, for a galvanic cell, you have to take the higher number as the reduced half reaction and the lower number is the oxidized half reaction. That is if I don't give you who is who. Now in this one we knew who was who because I told you the reaction. Alright, so hold off on finishing drawing for a moment. I'm going to finish our notes shortly. Okay, so if you're in the middle of something, finish what you're doing, especially if you're in the middle of that second drawing. I will ask, are there questions on how to approach this one? What are your questions?
So would you just make your method?
You mean when you say make your own, are you talking about a new electrode?
Just put in the
Yeah, yep, because this is all gaseous and aqueous. Yep. Question? Say again? It's telling you that these 2 are occurring in one half reaction at the cathode. but you need to decide on how to write that half reaction to make it reduce, because that's at the cathode. Questions?
So do you just assume that both gaseous,
No, you guys should know this now. Chlorine is gaseous, aqueous, right? Bromine is, I'm sorry, bromine diatomic is, what is it? Liquid. I gave you guys that one question back on like thermo, because most people didn't know that, but now we do. Bromine is liquid, and this is aqueous. So that's gonna be like a little puddle of bromine in your cell. Excuse me? It is liquid at room temperature, but I'll tell you what our standards are here in a second. You guys see these knots? I've been writing like a knot. That's standard conditions, which I'm going to show you what it is. Okay, so this is actually an interesting cell. This is the air cell they had like on the 2015 exam. It was weird, but we actually have a metal, and then we have oxygen as our other electrode. So there was an interesting question there. We'll go over that more. But just as a quick reminder, we do have to have an external wire to help with electron transport. If not, we can't do work. Work, like the definition of work, relates to Gibbs free energy. So remember that work and Gibbs free energy are related, because the definition of Gibbs free energy is energy available to do work. So there must be a mathematical relationship here, which we'll explore at the end of today. Thumbs up when I can move on. All right, majority rules, maybe. All right, take a minute and write this down and read, because there's some terminology here that's very important. I've spoken to you about it, but now we've got to make sure you have it down. Scroll down some, so you guys can see that bottom piece. I'm going to start explaining just to emphasize those parts, and then I'll scroll right back down to where you guys are. So, just the mentioning of cell potential is saying the potential of that galvanic cell to transfer electrons. Like you have the potential to get an A on your next AP Chem test. We're looking for potential here, like the ability to do so. So it does matter based on the two sides of the galvanic cell, so the two electrodes, because some are very willing to be reduced and some are not so willing to be reduced. So we do have to have this list of like who's really able to be reduced and who's not so able to be reduced, which is right in front of you, called the standard reduction potential list. Now, on a test, I will give you in question, like in the middle of the question, these are the reduction potentials. You won't have the big list in front of you. You'll just have just things specific to that question, so you're not looking through a big list. They used to give us a big list and they don't anymore. That's why I've kind of modified, but that's just for your homework and like other purposes. So the reduction potential, and I'm trying to verify we are all on board, this is reduction only. We call it E, but it stands for reduction potential. And we're looking for the tendency for the electrons to be moved from the anode to the cathode. But we're looking at it as a comparison, because we can't just compare it to themselves. We have to compare it to one standard. And that standard we compare it to is called the SHE, which is the standard hydrogen electrode. Everybody find that one on their little paper. Standard hydrogen electrode. Look for where it says hydrogen. Should be in the upper right hand corner. What is it, Qui? 0. So the standard hydrogen electrode, which is hydrogen ion plus 1 electron going to hydrogen gas. Is that right? So they don't have to balance it out with 2s. Okay. So that standard hydrogen electrode has a 0.00 cell voltage or reduction potential. So we compare everything to that. So if you're above 0, you're very, very, very likely to be reduced. So that's why we look at the number. If you're positive, you are likely to be reduced, more likely than the hydrogen cell potential. If you are below 0, that means you're not likely to be reduced, hence oxidized, but we know you're just not likely to be reduced. So I try to speak of everything in reduction because that's how all these values are compared, but we do know if you're not likely to be reduced, you're likely to be oxidized. That's just the counterpart to that. So we always have to have a number to find the cell potentials. Question? No, actually, you have to have the numbers, both numbers, you have to know their differences. So if you're more likely to be reduced and you're compared to something else that's also likely to be reduced, you're going to be a crappy battery because no one's going to give up electrons. But if you have something that's super likely to be reduced and then super not likely to be reduced, the bigger the difference in reduction potentials, the better the battery, the more voltage you get. So you really want like polar opposites here. So that's why I'm always saying the higher number is going to be the reduced side to the cathode, and the lower number is going to be the oxidized side or the anode. That's how we can pick if we're not told, hey, I'm the anode, you're the cathode. We have to pick our own. We do it based on on reduction potentials. So the term electromotive force, abbreviated as EMF, is that difference that we've been speaking of. So when I say cell potential, it means the potential of the galvanic cell to move electrons, which we call the electromotive force, meaning the force of electrons being transported, which is also referred to as driving force of the battery. 3 things mean the same thing, but so know your terminology so you're not mixing up like just the one reduction potential versus the difference. So whenever you're looking for a cell potential, we always label it E cell, which would give us clarity like this is talking about the whole battery. And then note, we've only mentioned reduction, just making sure you know that's very clear. We good here? Okay. So, like I've said, you guys have a big list, but I'll give you like snips of that. That makes it a little easier to digest. And the only time you would ever flip a number, like take a positive sign and make it negative, or negative make it positive, is if I said it in a multiple choice question. What would be the oxidation potential of this reaction? So it's the opposite. So we really will do that like 1/1,000,000% of the time. But if it ever asks for something like that in multiple choice, all you do is flip the sign. But other than that, you will never, ever flip a reaction or flip a sign, okay? Okay. So at the top of the list, I have all these positives, which mean they're likely to be reduced. You'll notice that fluorine is really high up here. Why does that make sense for fluorine? It's really electronegative, right? So if you're really electronegative, you are super, super likely to gain electrons. So then who do you think's at the bottom? Okay, so I hear francium. Francium is very hard to come by. So it's not something that we'll always use in batteries. There's another one in group 1 we mentioned yesterday. Lithium, good. So lithium's pretty low. I don't think francium's on this list. No, so lithium's pretty low at a -3, which means that it's not likely to be reduced, meaning it's likely to be oxidized, which means it's likely to give up electrons. We know that oxidized means it gives up electrons. And then there's hydrogen here as our comparison point in the middle. Good here? Yeah. Actually, no, that would be a fantastic battery, but lithium fluoride would have to be like an electrolytic situation. And we have lithium batteries, which have been such good batteries they catch on fire, like what Samsung, what was the battery? Okay, so some lithium batteries are fantastic. They're well controlled, but lithium itself is so reactive with water that I don't think they trust it in the consumer hand. But yeah, lithium being a -3 and fluorine being a +2 would be 2.8 minus a -3. That would be like a 5-volt battery just from like 1 mole of each of these, which would be good, really good. So yes, the bigger the difference, the better the battery because we get more cell voltage. Okay, so another one, all right. Another one, but with respect to the activity series, but which we know now activity means what? Or active means what? Give up electrons, which means you're going to be oxidized. I was going to say oxidized. Okay, so remember at the top of the activity series are all those metals that give up electrons. So just remember that means oxidized. Cool? Okay, that's really the point of this one slide. Active gives up electrons, which means oxidized. Okay, so we spoke of like how to find cell potential, but these are how it's going to be varied. So take a minute and write down what will vary or what will cell. This is a good multiple choice based question. It could say like which of the following would impact E cell, or which of the following is E cell dependent upon. While you guys are writing, we're going to try to do a portion of our simulations now for some people who have laptops. These 2 tables can use my laptops. Middle 2 tables, you guys go grab your laptops. Yeah, that's you guys go see. And last 2 tables, go grab your laptops. All right, back with me for a minute while you're still writing. I'm going to explain the main pieces here. So whenever we write the not, it's speaking to standard conditions because as you can imagine, now we know that as concentration of the solutions inside the chambers differ, E cell could differ. So we have to have one standard for our concentrations to use as a comparison, which is what's on those standard reduction potential list. So the standard for concentration is what? 1 molar, right? That is the standard for concentration. As the concentration varies, we have to have another way to calculate E cell, which is called the Nernst equation. We'll look at that tomorrow. But the Nernst equation offers us a method to find E cell for non-standard conditions. the composition of the electrodes, duh, that's what we've been looking at, like silver and copper and, chlorine and chromium. We need to know the composition of those electrodes or their species involved so we could actually look at the ones to subtract. So we would have the standard reduction potential list, so that's why you have a table. And then all of these half reactions are reduction, so check, we've seen that now. We've said that 5 times at this point. And then the greater, this is the piece that I've been explaining to a couple of you guys based on your questions. The greater the E cell, the greater the E, the reduction potential, the blank, the oxidizing agent. Better or worse? So if it's bigger value of reduction potential, that means it's got a high or low potential to be reduced. A high potential to be reduced. Okay. Remember, reduce means you are the you are the oxidizing agent. So if you have a high potential to be reduced, would you be a better or worse oxidizing agent? Better. You would be a better oxidizing agent. Just meaning that you are really good at yourself being reduced. And then this is our last reminder. Cell potential is just the relative ease to move electrons between the anode and the cathode. Give me a thumbs up when you're good here. I know some of you guys were still getting logged on. Just go ahead and get logged on when you're waiting on me there too. I think I'm almost done. Oh, sorry. The rest of these are important too. I only highlighted the molarity, but room temperature 25 degrees Celsius, 1 atmosphere is the other piece of the standard condition. So those are what we have as our notation when we put not. Yeah.
Is E cell, is it independent of temperature?
No. I mean, yes. No, it is dependent upon temperature because that's why it's dependent that it's at 25 degrees Celsius. That's the standard condition. So as you change temperature, E cell can change. Because as you change temperature, things move faster or slower, so therefore electrons move faster or slower, so the voltage will change. Okay, so I've got a couple more reminders. And some of these are on your notes if you've been looking, but otherwise these are also pieces that will help you decide how to modify E cell or cell potential. Coefficients do not change anything. Coefficients are just for us to balance electrons or for us to balance equations. What does intensive mean? So it's, amount doesn't matter, meaning if I have a huge galvanic cell or a small galvanic cell, the size of the electrode doesn't matter. It's more about the surface area, actually. But the size of the electrode does not matter, so the E cell is just based on those conditions we mentioned previously. And it's not determined by the number of electrons transferred, like, you know how we usually balance with coefficients? And we'll say, like, oh, 2 are transferred here, 3 are transferred here, but so that's a total of 6. That does not affect E cell. E cell is voltage, and we mentioned voltage yesterday. Voltage is amperes. Okay, well, okay. Current is amps. Sorry, let me go with current. Amps, which is what per what? Coulombs per second. So we always base it per time, so that's why the number of electrons don't matter. And then I keep saying redox, so reduction half reaction minus oxidation half reaction. It's also the cathode minus the anode. So if I ever write it in another notation, it's the same thing. And then the greater the E cell, the better the battery, because there's a greater force of electrons flowing. So we want a big difference between reduction potentials to make a better battery. So this basically means the greater the E cell, meaning more positive, the delta G. The more negative, I'll even put more negative so it doesn't seem like I'm saying it's smaller. The more negative the delta G because it means it's more spontaneous or thermodynamically favorable in that direction. Okay, make sure you're going to my website under homework for me. And go to today in like the little agenda on the bottom. I'm going to leave this here for a second for some folks to finish writing down if they need to. Click on what's the simulation under like day 2. It's like in the like boxed agenda. I think I'm done for now. Yeah, you guys can do that. So we're going to get started on probably one section for now, which will be okay. We'll do the rest of it. Oh, no, tomorrow. So So right here under day 2, we'll review our homework tomorrow, but activity simulation, concentration cells, metal activity series, etc. So when you click there, you pull up a Google Doc, and there's part 1 through infinity. So I want you guys to try to do part 1 right now in like 15 minutes. When you click on this, it's going to ask you to investigate 2 metals. So like follow the steps in the diagram, choose 2 metals, and surrounding by each metal with its own ion solution, write your metals. So it's walking you through to make sure you can draw a galvanic cell. And then down here, it tells you to do a couple of other activities. We will probably not get to this today, so I'm going to hold off on the second part. But I do want you to start on the first part, and then tomorrow we'll work on a couple more of these. Because the third part is just exploring so that you understand the differences between Gibbs and work and electrical transfer. Because these are variables that we're going to speak of tomorrow. So right now, I'll start on part 1. If it gives you a problem with Flash, you have to say allow. Okay, you have to say allow. So click to allow Flash Player. So if you want to look on with somebody so you can like work together, that's fine. It might be easier to look at one person's computer and talk. So you can have natural partners at your table someplace.